So we're going to take a look at Chapter 7 for Exam 5, review. I'm going to use the review document. And true to form, I have some marked out. Since we have a lot of time, I may pick some that aren't marked, right, just to round out the picture. In fact, the first one, let's take a look at that first one. When ignited, a uranium compound burns with a green flame. The wavelength of the light given off by this flame is greater than that of. So if it's green, it's on the spectrum here. Let's see. So we got visible in here. I think the way we had it set up before was the wavelengths increased this direction. Somebody popped in. Let's see who it is. Kathy. All right. So we're only missing Alexis now. The way we had it set up was the wavelength increased this direction. So that means the frequency increased that direction. Okay? And that means the longer wavelength is the red end of the spectrum. Shorter wavelength is the blue end of the visible spectrum. Okay? And now remember what was on this side of the spectrum. This would be ultraviolet. Yeah. Blue's in here, violet's right there. So we call that ultraviolet. And then we went to X-rays, correct? Then we went to gamma rays. Okay. These are the most energetic of all. Energy also increases this way, based on Planck's equation. Remember Planck's equation? E equals Planck's constant times the frequency. So I'm just trying to get oriented here so we can answer the question intelligently. On this end, we have infrared. And then we have, what do we have next? Microwave. And then we have radio waves. Radio waves. Now, the radio waves are the longest wavelength, the lowest energy, and the lowest frequency. Okay, now let's see. The question is, the wavelength of light given off by this flame, which is green, right in here somewhere. The wavelength of light given off by this flame is greater than that of. So the wavelength here would be greater than anything on this side because of the way the wavelength, the way we have it set up, the wavelength is increasing this way. Some manuals, some textbooks, you'll see it flip the other direction, which is all right as long as they're in the proper order and you know which way is increasing and which way is decreasing. But if we want this wavelength to be longer than anything else, it'll have to be one of these, UV, X-ray, or gamma. So which ones do we have? Well, let's see, red's on the other end, right? So it can't be. Infrared's on the other end. Radio waves on this end. Ultraviolet's on this end, right? So there's one choice. What else do we have? Yellow light. Well, what is it? It's red, orange, yellow, green, blue, indigo, and violet. Give Roy G. Biv backwards. So yellow's on that side. So out of that list, ultraviolet's the only one that satisfies. It's a shorter wavelength. The green is a longer wavelength than this one only out of that list. Okay. Let's see, I'm going to leave that there for a second because we might need it again. How about number 2? All right. Which form of electromagnetic radiation has the longest wavelengths? Okay, so we're looking at this end. Out of that group, won't be gamma. Gamma has the shortest wavelength. Microwaves, right? They're pretty long. Radio waves are longer though. Infrared's on this side, X-rays on that side. So radio wave would be the longest wavelength. Like C. All right. Let's see here. 3. Which of the following frequencies corresponds to light with the longest wavelength? Right? The longest wavelength is the shortest frequency, or the smallest value for frequency. All right, so we just need to look for the smallest value of frequency out of that group. And if we've got A through E, first thing I would do is look at the powers of 10. Since this is in the scientific notation, just look at the powers of 10. Which one has the smallest powers of 10? And it looks like the smallest one is this one, 4.12 times 10 to the 5th reciprocal seconds, right? That's the proper value if you want to do any cancellations or multiplications of this with something else. But we also call that hertz. All right, so that's the smallest one. The longest wavelength is the smallest frequency. So the smallest frequency would be this direction. We don't know where it is in here because we don't have a relative comparison of that value, but we know that out of those, it has the smallest wavelength, the longest wavelength, smallest frequency, shortest frequency. All right. That was 3. Let's see. Well, we could do 4. It pairs up the symbols. Now, sometimes it's good to go back to basics. Wavelength, is that correct? Is that the symbol for wavelength? Yep. Small lambda. Frequency. Right? Yeah, that's frequency. Speed of light. Yep, that's it. Hertz. Reciprocal seconds. Yeah. X-rays. X-rays. Do X-rays have the shortest wavelength? No. X-rays don't have the shortest wavelength. The shortest wavelength is gamma rays. So it should be the Greek, the Greek gamma ray has the shortest wavelength, or the highest frequency. So E should be the answer for that one. All right. We're going to skip this one because we did one kind of like that already with the uranium. Now we'll go to 6. Yeah, I hesitate to erase that. I wonder if I'm going to need it again. I guess I can redraw it if I need it. Because if we're going to be doing calculations, I'm going to need board space. Number 6. A line in the spectrum of atomic mercury has a wavelength of 254 nanometers. So if the wavelength of mercury, and this is just one of the wavelengths, there's several of them, but the one that they're giving us is 254 nanometers. When mercury emits a photon of light at this wavelength, the frequency of that light is. So we're looking for the frequency of light. If the wavelength is that value, right? So how are these two related? Remember that? Speed of light equals wavelength times frequency. Okay? So if we're going to get frequency, we need to solve for this one, which would be C divided by lambda. Now we have to consider the units of measure. right? The units of measure here, let's just put the value in. 2.9979 meters per second. Oh, excuse me. I left out a power of 10 times 10 to the 8th meters per second. I believe that's right. And the wavelength, though, has to be in meters. Okay, so how do we convert 254 nanometers to meters? You take that prefix right there. What does the N, nano, mean? It means 10 times 10 to the minus 9th times 254. And your calculator will accept that. Right? So you don't have to change it, really. Well, it's this exponential notation. Remember, it's not scientific notation. 254 times 10 to the minus 9th meters. So that way, denominator, numerator, the meters cancel, and the denominator gives us reciprocal seconds, and that's what we want. And so all we have to do now is divide those numbers and hope I did everything right. 2.9979 exponent 8 and 254 exponent minus 9. And I get frequency equals 1.1. This one limits it. 8 times 10 to the 15th reciprocal seconds or hertz. So that's C. Okay. That's one of those easy, well, it's a one-step calculation. You just have to be careful with this one up here. Got to be changed. Got to watch out for those units of measure. Those will trip you up.
Yeah.
Okay, let's see. Let's do number 8. Green light can have a wavelength of 543 nanometers. Wavelength. The energy of a photon of this light is. So now we're looking for energy. I put that equation up there a little earlier. This is Planck's equation. But we have wavelength, we don't have frequency. So you have two choices. You can use this equation and convert wavelength into frequency and then plug frequency in here with Planck's constant. And Planck's constant will be on the exam, right? It's in the useful information. Yep. There it is. Or we can solve this one for frequency, and C over lambda, and plug it in here. Like that. Then all we have to do is be sure that this is in the correct units. And so that'd be 543 times 10 to the minus 9 meters. So that way we can do this all in one single calculation. Planck's constant, I have to read it out myself. 6.626 times 10 to the minus 34 joules seconds units. And then we have speed of light, 2.9979 times 10 to the 8th meters per second. And then the wavelength is 543 times 10 to the minus 9th meters. Okay, so meters cancel. This is in the numerator, that's in the denominator. Seconds cancel and leave us with joules. So we're good. Joules is our energy unit. Now what we have to do is crunch numbers. We've done all the thinking we need to do. 6.626 exponent minus 34 times 2.9979 exponent 8 divided by 543 exponent 9, negative 9. So I get the energy of that photon with this wavelength. Let's see, three significant figures. 3.66 times 10 to the minus 19 joules. That would be C. Okay. And number 8. We good? Okay. All righty. Let's see. We've done one like that before. We've done that one before. So we're down to number 11. I think I need a new marker. See, do I have one? I like black. Black shows up better in the video. 11. Okay. How many of the following are correct? Oh, okay. So we've got out of these, the importance of the equation equals mc squared is that energy has mass. Yeah. Yeah. That one's correct. Energy does have mass. Mass has energy. They're interchangeable, according to Einstein's equation. Electromagnetic radiation can be thought of as a stream of particles called photons. Oh, yeah. Yeah. That's true also. Right? Where do we see that? Where do we see evidence for light being particle? Let's see, what was that thing we talked about where you had the metal surface and light coming in and then they ejected the electrons? Nobody remembers? Okay, we'll move on. We're going to see it again anyway. Electromagnetic radiation exhibits wave properties. Oh, yeah. Right. I'll go ahead and tell you. Give a well-rounded picture. Photoelectric effect. Okay, how about this one? Where do we see evidence for wave properties? There are a couple of possibilities there. Diffraction. When light encounters a barrier, or when light tries to negotiate a small opening. How about refraction? Think lenses. Right? When light passes from one medium to another, it's bent. The example I showed you was going from air through, I think, glass. So the denser medium, glass, causes it to bend toward the vertical. Light coming in like this is bent toward. This is the normal right here. And this is the angle the angle of incidence here. And it doesn't bend quite that much. Maybe like this. Going down here like this. This is the angle of refraction. Okay. So this one, in this case, for glass and air, then it's going to bend toward the denser medium. If it came the other direction, right, it would be, let's see, it should bend the other way. When it goes from the denser to the less dense, it bends the other way. But that's refraction. And these are both evidence for wave properties of light. How about the last one? Energy can only occur in discrete units called quanta. Yep. Light gives us evidence for that in the photoelectric effect, but also we see it in atomic emission spectra, where the electrons can only move from one place to another, right? There's no in between. You got to have the right amount of energy to go from one level to the next, either increase energy added to the atom or give up for emission. The electron moves from a higher level to a lower level and emits a photon of radiation. So all of them are true. All four of them. All righty. We can take our time because I don't expect to get finished today, and we can come back Tuesday and finish up. We'll have lots of time because we don't have a lab on Tuesday. I couldn't find a really good lab that worked off of these principles. They're probably out there. I just couldn't find one. Maybe that ought to be on my bucket list. All right, so we're given this table from the following list of observations. Choose the one that most clearly supports the conclusion for the following four questions. All right, so we're going to choose from A through E, A, B, C, D, E, to address the questions or the statements that are in 12 through 15. Okay, so how about the first one? Well, all right, statement is electrons have wave properties. Electrons have wave properties. Which one of these? Okay, so this should be fresh on your mind because I just talked about it. Which of these demonstrate wave properties? Emission spectra? No. Photoelectric? No. Scattering alpha particles by metal foil? No, it has nothing to do with light, right? That's talking about the Rutherford's experiment, the nuclear model for the atom. We did talk about that earlier, didn't we? Oh, maybe we hadn't got, we should have got there. Yeah. Diffraction. There you go. Diffraction speaks to wave properties. So that would be D. Cathode rays are not light. Cathode rays are electrons. Right? That was J.J. Thomson's work. All right, so 12 would be D, right? Diffraction. How about 13? Yeah, scroll just a little bit. There we go. Electromagnetic radiation has wave characteristics. Well, okay. Actually, my explanation for this is light has wave characteristics. Diffraction also works there. Electrons have wave characteristics because electrons have mass, but they also have energy. Right? And we don't have the best description of wave properties for electrons is not in that list. The best explanation for is actually diffraction for electrons is demonstrated in the electron microscope. If you've had either microbiology or anatomy and physiology, maybe in biology class, you've used the microscope, right? Light microscopes. So you know that they have a limit. They call it the diffraction limit for light microscopes. You can only see down to a certain size particle or cell, but you can't see any smaller because the light won't let you. You need a shorter wavelength of something in order to get down and see things that are that small. And that's where the electron microscope comes in. Because the electron microscope fires these electrons at high velocity, and we can interpret them and actually manipulate them using their wave properties. And when they strike the object, they diffract from that object in as a smaller size. So they have a lower diffraction limit, electrons do. So that's the best explanation I can give you offhand. But yeah, both electrons and light have this diffraction characteristic. How about electrons in atoms have quantized energies? What's the best explanation for that? Say it again. Electrons in atoms have quantized energies. What does that mean, actually? That means if you have a nucleus here and your electrons here, your electrons can only occupy energy levels at discrete positions. There's no in between. That's called quantizing the energy levels. So where do we see that in this list? Let's see, emission spectrum of hydrogen. Yeah, that's where we were introduced to it, right? Because the emission spectrum for hydrogen in the visible range only has 4 lines. It's a line spectrum of 4 wavelengths. None of the others fit. Just that one. So this one's A. And 15. I think that's the last one. Spacing between atoms in a crystal is the same order as the Broglie wavelength of accelerated electrons. Okay. Spacing of atoms in a crystal. We haven't talked about crystals yet, but crystals have a very regular structure of atoms. It's a solid where the atoms are locked in position in a regular arrangement, and we can think of them as stacked in layers. All right, so when we look at the distance between the layers, the distance between the nuclei in the layer, this distance in here is on the order of the wavelength of that electron. So if we fire electrons at it, it diffracts in this space. Okay, so the best answer for that one is diffraction. That should also be D. So I guess I'm springing some new stuff on you during our review. It's not like I haven't done it before, right? Get the basic concepts in lecture, and then we try to apply them in the review. Okay, 16. The 4 lines observed in the visible emission spectrum of hydrogen tell us that, well, let's see, hydrogen molecules came from the formula H4. No, we're talking about individual atoms. This emission spectrum is derived from individual atoms in a discharge tube. We could observe more lines if we had a stronger prism. I kind of doubt it. In fact, it's been tried, right? Very efficient. In fact, before the invention of the diffraction grating, prisms were all we had for splitting light into its component wavelengths. So we would take a prism and shine light through it, and it would split. That. Now, it's entirely possible that in some cases, hydrogen is not a good candidate because it's only got 1 electron. But for polyelectronic elements, sometimes the wavelengths they're very close together, and one prism won't get them apart. So we take another prism and we stick it right here, right? And then it splits them again. But in the case of hydrogen, that won't work because hydrogen is so simple with one electron. Those four lines are all you can get from any prism, any combination of prisms. C, there are 4 electrons in an excited hydrogen atom. How did that happen? How do you get 4 electrons in a hydrogen atom? You don't. It's a stupid proposition. That's the best I can do. D, only certain energies are allowed for the electron in the hydrogen atom. That's the best interpretation. Only certain energies are allowed. So when the electron jumps from one energy to the other, when it jumps from a higher level to a lower level, nothing in between, it gives off that wavelength of light. And the spectrum is continuous? No. If it were continuous, you wouldn't have separate lines. 4 lines in the visible spectrum means that it's not continuous. So the best one for 16 is D. All right, 17. For which of the following transitions does the light emitted have the longest wavelength? It's the longest wavelength. What does that mean about energy? Think of it in terms of energy. Longest wavelength means the smallest frequency, right? Which also means the smallest energy, because energy equals Planck's constant times frequency. Right? So if we make this small, this has to be small. Okay, so the smallest energy means what? It means the electron jumps the shortest distance from one energy level to the next. So the transition here, A, B, C, D, E, yep. And it's jumping from this end to that end. This end would be 4 to 3, 4 to 2, 4 to 1, and 3 to 2, and 2 to 1. So the electron's jumping from a higher level to a lower level. Which one has the shortest distance of a jump? Well, it's good to draw a picture for this one. If this is the nucleus, and this is n equals 1. N equals 2 is way out here. Then n equals 3 is closer, and 4 is even closer, and 5 is even closer still. So the shortest jump, there's not a 5 up there, is it? Okay, so we can ignore 5. If we jump from 4 to 3, it's this distance here. If we jump from 4 to 2, it's this distance. If we jump from 4 to 1, it's that distance. If we jump from 3 to 2, it's this distance. If we jump from 2 to 1, it's that distance. So which is for the longest wavelength, which one is the lowest, shortest energy, smallest energy? It will be a jump from here to here, 4 to 3. 4 to 3 is the shortest distance that in terms of energy, that electron can move. Right? So A is the answer. 4 to 3 gives you the least amount of energy, which translates into the smallest frequency or the longest wavelength. Let's see. Yeah, we're going to stop at 18. Okay. When a hydrogen electron makes a transition from n equals 3 to n equals 1, which of the following statements is true? An electron is going from n equals 3 down to n equals 1. Energy is emitted. Right? Remember, the closer you get to the atom, the lower your energy. So if you go from this higher energy to this lower energy, Oops, it's not a good wavelength. There we go. You give off energy. You emit energy, or the atom emits energy. Okay, so Roman numeral 1 is true. How about 2? Energy is absorbed. Well, it can't be both. How about 3? The electron loses energy. Yes, it's going from higher to lower energy. So 3 is also true. 4, the electron gains energy. Right, can't be both again. The electron cannot make this transition. Who says? Not me, right? Not every scientist since it was proposed by Niels Bohr. So 2 and 3 together, 1 and 3, excuse me, 1 and 3 are the best answer. That's B. Okay. Alrighty. 18, we're going to skip down to squeeze 21 and 22 in there. I haven't seen any that are fresh, so I've been skipping to the highlighted ones. Which of the following is incorrect? Pay attention to the question, right? If I throw a correct or an incorrect in the statement, be sure that you know what the question is. Which one is incorrect? Which means that only one of them is incorrect because we don't have any of those squirrely ones in there, like none of the above, 2 of the above, all that stuff. Each one is a unique answer, so we only have to look for one. Just find one that's incorrect. So how about A? What's the A say? The emission spectrum of hydrogen contains a continuum of colors. We found it, right? That's the bad one. That's the incorrect one. The rest of them are correct. Let me see if there's anything that can be taught from these. How about B? Diffraction produces both constructive and destructive interference. All right. Have we talked about that? Constructive interference and destructive interference. I think we have. In fact, I think we had a video on it. Right? When you look at waves, right? If they're synchronized, they're perfectly synchronized like this. And you put those two waves together, you combine the two, right? This is up at the same time. You're going to get something like this. Oops. That was a bad drawing. How about this one? And there we go. And there we go. Something like that. So you get constructive interference. However, if the two light waves are perfectly out of sync and they go like this, right? You add those together, the crest here meets a trough there, that equals perfect destructive interference. You get nothing out of it. This is the whole idea behind noise canceling headphones. Anybody got a pair of those? Okay. What they do is they actively measure the sounds that are coming in from ambient, and they produce a pattern of wavelengths that's exactly opposite to what's coming in, and it cancels them out. That's destructive interference. Then you can hook up your headphones to whatever you want, and since the source of the vibrations are internal to the headphones, then the external mechanism doesn't see them as ambient noise and lets you hear them rather than anything that's ambient. So you could be right next to a jet engine with those things on and listen to, I don't know, one of my favorite, Beethoven's Sixth Symphony. Okay, that was 21. 22. Which of the following statements best describes the Heisenberg uncertainty principle? Remember Heisenberg? I wonder if I can remember Heisenberg. I can remember the formula that I gave you, right? Change in position, change in momentum, and momentum is mass times velocity. So either one of those is good. Is less than or equal to Planck's constant over 4 pi. I believe that's it. Is it less than? I don't know if I have it in useful information or not. Let me see. Is it there? Is it there? No, I don't see it. I hope I did that. The only possibility here is that I got this reversed. It's possible. So in words, though, the exact, A says, the exact position of an electron is always uncertain. No. You can tell where an electron is. If you tell where it is, you can't tell how fast it's going. You can't tell what its energy is. So that's wrong. The velocity of particles can only be estimated. No, that's wrong also. If you estimate the velocity of the particle, you don't know where it is. This seems kind of counterintuitive, right? Because how are you going to measure the velocity of something if you don't know where it is? That's what the law says. And that statement is incorrect. It's impossible to accurately know both the exact location and momentum of a particle. Bingo. That's Heisenberg's uncertainty principle. And it becomes more problematic the smaller the particle. That's why at the atomic level, this expression rules the roost. Okay, that was Heisenberg 22. Let's see, we'll just put 25 and 26 together. We're doing on time. Okay, I got a half hour. That's why I've been digressing so much, because we've got all the time we need. How many f orbitals have the value n equals 3? N equals 3. All right. What are the possibilities? If the principal quantum number is n equals 3, how many other quantum numbers do we have to describe an electron? We have 3 more beyond this. Remember what they are? Principal quantum number, what's the name of the next one? Angular momentum quantum number, magnetic quantum number, and spin quantum number. Okay. So what are the possibilities? Well, if this is 3, then the possibilities for L, we start at 0, and we go to n minus 1. Those are the possibilities, right? Now, this calls for describing the f orbital, right? So we have letters assigned to the L's, right? S, P, D. Where's the F? There is none, right? If n equals 3, you don't have f orbitals, right? That's why the answer is 0, A. All right. Let's look at 26. I think it's along the same lines as this one. 26. How many f orbitals have n equals 6? Now we got possibilities. How about L? Well, let's see. Well, first of all, this is also called a shell. Many books call that a shell. This is a subshell. And this is an orbital. All right, so when this asks for how many orbitals, we're saying how many of these can it have? How many f, or, well, no, they're calling f, we're calling these orbitals. All right. If n equals 6, then L can be 0, 1, 2, 3, 4, and 5. So this is S, P, D, F, G, and what's 5? I think 5 is H. So how many? Yeah, okay, F orbit, that's right. So we have a 3 here. Now we can go from 3 to M sub L. All right? Remember how we do M sub L. We take this number and we go from negative L, negative 3, and then we increment it in whole numbers up to positive 3. Minus 2, minus 1, 0, plus 1, plus 2, plus 3. There we go. So those are the number of orbitals. All right, they had it right the first time. All right, 1, 2, 3, 4, 5, 6, 7. We have 7. In fact, that's the same for all F's. All F's have 7 orbitals possible. Okay? That would be B. Now, while we're here, how many possible electrons can we have? If we can have a plus half and a minus half, 2 electrons for each one of these, you can have 14 electrons. Right? That's why, let's see, you guys can't see it, but that's why the lanthanides and the actinides, this list has 14 elements in it. Because we're filling F orbitals in the lanthanides and the actinides. All right, that was 26, 27, and 28. Okay. 7. If n equals 2, okay, how many orbitals are possible? Right, in this case, we have to work our way down. Right? L equals what? 0, 1, and 2, correct? Now, M sub L. So we have to take each one of these. How many M sub L's can we have from this one? We can just have 1. How about this one? This one we can have a minus 1, a 0, and a plus 1. Okay? This one we can have minus 2, minus 1, 0, plus 1, and plus 2. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Isn't that right? Did I do that right? Let's see. 0, 2, 5, 6, 7, 8, 9. So we have 9 orbitals. Why does it say only 4? Oh, nobody caught me. Did you see my mistake? No. I put too many L's in there. We can only have work our way up to n equals 1, n minus 1, right? 0, 1. Your instructor's not as sharp as you thought he was. Your instructor's not as sharp as he thought he was. Okay, so that's right. We have 4 orbitals with n equals 2. Maybe that'll help you remember it. That's the one that my instructor screwed up. I'll never forget that one. 28. Let's see. A given set of p orbitals consists of given set of p a set of p orbitals. Right. So if we have p, L equals what? Well, if it's S, it's 0. If it's p, it's 1. So if we have 1 as our p orbitals, as our subshell, how many orbitals can we have from that? Right. Minus 1, 0, and plus 1. And so you can have 3 orbitals for L equals 1 or a p. All right, that was 28. 29. Which of the following is an incorrect designation for an atomic orbital? All right, let's put all of them up here so we can work on them. Down to E. Okay, they're telling us that's an orbital designation. And this is an orbital designation. This is an orbital designation. And this one is, and this one is. Okay. And the way I approach this is I take them SPDF. And I look at the S's. Okay. We look at the S's first. Can we have a 6S or a 1S? Yeah. This is 1. N equals 1. N equals 1. So we can have an L equals 0. N minus 1. Right, that's valid. The same thing works for here, right? When we get out to the sixth principal number, you can have S, P, D, F, G. Yeah, you can have those 5 because that's 0, 1, 2, 3, 4. Actually, we can go to 5. Right, so you still have an S orbital in there. So that's, yeah, you can do that too. So this one's okay, and this one's okay. Right? How about the next one? How about P? Right, we got a P right here. Okay, can you have a 1P? No, no, because the L can only be 0. That's an S. A P has to be a 1, and we don't have a 1. So we found the bad one. This one right here. Okay, the rest of them are valid. Okay, 29. Let's see who's next. 31 and 32. 31. Let me see. Be sure I haven't missed anybody. My paper, here we go. Alexis still hadn't shown up. Okay, 31. A point in the wave function where the amplitude is 0. Right? What? Remember the wave function? And we use psi squared. These are Schrodinger's equations. The wave function and we used a visual cue reference for this. The place where the wave function goes to 0 is called what? That's a node. A node. All right. That's just definition. Memorize it. No easier way. 32. How many electrons in an atom can have a quantum number, have quantum numbers n equals 3, L equals 2? So if n equals 3 and L equals 2, how many electrons can that atom have? Oh, yeah, how many electrons can there be? Okay, if n equals 3 and L equals 2, then this is fixed. This is fixed. Now we have to go to M sub L. So M sub L could be a -2, -1, 0, +1, +2. And each one of these can have 2. Right? So we have 1, 2, 3, 4, 5 times 2 plus 1/2 minus 1/2. So we can have 10. That's why the answer is C. 10 maximum. 33 and 34. All right. How many electrons can be described by quantum numbers n equals 3, L equals 3? Let's see. N equals 3, L equals 3. M sub L is 1. M sub L. 1. Well, let's see if it's valid first. Can L be 3? L could be 0, 1, or 2. Right? No electrons. You can't have that. It's forbidden. Quantum mechanics says, nuh-uh, no way. How about 34? What is the L quantum number for a 4s orbital? What is the L quantum number for a 4? Oh, if we have 4s, is it? Yep, 4s. Which one's L? This one's N, this one's L. So the quantum number for this one is 0. Right? That's what it just goes back to S, P, D, F. These are the ones that we're gonna need for building atoms. Beyond that, anything beyond 3, L equals 3, or F orbitals is an excited state. We don't build atoms past F in the neutral state. They have to be excited. Ground state, I should say. These are ground state orbitals. Anything beyond that would be excited states. There are probably some people trying to build neutral atoms, ground state atoms with G's or beyond, but that's not where we are in the periodic table. Okay, 37. Which of the following combinations, let's see, I'll read it from the back. Numbers N, L, M sub L, M sub S do not represent permissible solutions of the Schrodinger equation for the electron in the hydrogen atom. Which combination of quantum numbers is not allowed? All right. So let's see. D. E says all are allowed. Okay. All allowed. The first one, 9, 8 minus 4, 1/2. 9, 8 minus 4 plus 1/2. So this is the N's, this is the L's, this is the M sub L's, and this is the M sub S's. So B is 8, 2, 2.5. 8, 2, 2.5. And 6 minus 5 minus 1 and 1/2. And 6 plus 5 minus 5 and 1/2. And the question is, which of the following combinations do not represent permissibles? We want to find the bad ones. Right. And if we find none, then they're all allowed. But if we find one, we found our answer. Okay, is this one allowed? Well, we could look at this end right here. All these are positive 1/2. Those are allowed under any circumstances. Right? So we don't have to worry about these guys over here. We need to look at these three. So if this is 9, is 8 allowed? Yeah, it's n minus 1. That's the highest one you can get. Right? So if this is 8, how are these allowed? Minus 8, minus 7, minus 6, minus 4, 5, minus 4. That's allowed. So that one and that one is allowed for this one. And of course that one is. So this one's good. How about this one? 8 is 2 allowed for the L. Yeah. Mm-hmm. Yeah, it goes 0, 1, 2. So this one's good. Right. How about 2 out of this one? It would be minus 2, minus 1, 0, plus 1, plus 2. That one's allowed also, right? So this one's good. How about this one? 6. Is -5 allowed from here? No. It's 0, 1, 2, 3, 4, 5. Right. That one's not allowed. We found the one. We can go ahead and look at this one, but it's irrelevant now because this is multiple choice. We found the one. So that's the bad one. All right. Number 40 coming up. We have 10 minutes. Maybe I can get a couple more in before we have to depart. Or I have to depart. I can't stay late today. Who was the first chemist to recognize patterns in chemical properties of the elements? Patterns. What do we mean by patterns? Well, think of, they say patterns in chemical properties. So if we're thinking of a pattern in a chemical property, elements that have similar behavior, physical and chemical behaviors, right? Who first recognized that, right? This person created a list or a table of triads, 3 elements that had similar behaviors, right? That was Dobereiner, right? D. Dobereiner. I can't remember his first name, but he was obviously German. All right, 41. Mendeleev. He was a Ruski. Actually, he was Russian, right? Long before the commies came in. when Russia was still progressing toward a stable modern economy, right? Mendeleev was active. It wasn't until after the commies came in that Russian culture and scientific advancement went through like that. That's another topic. Mendeleev is given the most credit for the concept of the periodic table of the elements because. Remember why? Then we can go looking for the answer. Well, he put things in groups just like Dobereiner did. Right? But, and actually, Meyer and Mendeleev were active at about the same time. And they built their periodic tables with these characteristic groupings of elements with similar behavior. The reason that Meyer didn't get so much credit for his and Mendeleev got more credit was that Mendeleev set up his table so that there were missing elements. They didn't fit the pattern, so he left those spaces blank. And he didn't just do that. He predicted what those elements would be like, what their characteristics would be like when someone found them in the future. And he nailed every one of them. There were several of them. I don't remember how many. But that's why he gets most credit, because he used his periodic table to predict the existence of undiscovered elements. Now we've discovered or created 118 of them. That's as far as we've gone so far. Right? Adamantium notwithstanding. Right? Wolverine was supposedly some type of metal that we don't have on the periodic table that he got injected into his bones, and that's why he can cut through anything with his claws. Okay, back to the topic. Which one of these matches? B, he emphasized the usefulness in predicting the existence and properties of unknown elements. That's it, pure and simple. That's why he gets most of the credit. And Meyer was just kind of a footnote because he didn't do anything with his table, at least not this way. And guess what Mendeleev's profession was? Well, he did a lot of things on the side, but he was a teacher. All right. 44. Let's see. I have 5 minutes. 44, the complete electronic configuration of 10. All right, so what's the symbol for 10? It's one of those that doesn't match the English letters. Nobody knows. I had you memorize these. Take a wild guess. Starts with an S. SN is 10. It's derived from the Latin stanum. Okay, so how are we going to do the electronic configuration here? Well, first of all, we need to know how many electrons there are in the neutral atom. We look at the periodic table, and there are 50. Then we look at our answers. We don't have any shortcuts in our answers. Our answers are all complete, all the way from 1s out to whatever. So what we've got to do is put together our orbitals in the correct energy order. Lower energy left, increasing energy to the right. I have memorized 2s, 2p, 3s, 3p. Then we go to 4s, and then 3d, and then we go up to 4p. Okay? Now, how do I know that? Well, you can use that diagonal diagram, and it's in useful information. Or you can use the periodic table. Right? If you follow the periodic table from hydrogen to helium and then go down to the second period and go lithium, beryllium all across, the first two are 1s, right? Hydrogen, helium. And then the second two are lithium, beryllium. Okay. And then the next 6 are boron, carbon, nitrogen, oxygen, fluorine, and neon. Right? That gets you to neon. Then we drop down to the third period, right? 3s. You got 2 of those elements, sodium and magnesium. And then you jump across, because there are no transition elements in the way. So you jump across to aluminum, silicon, phosphorus, sulfur, chlorine, and argon. And that gets you the next 6. Okay? Then you drop down to the fourth period, potassium and calcium. That's 4s, right? Fourth period, 4s. Now we're going to cross over the transition elements. And when you get to the transitions in the fourth period, you have to drop back to a 3. All right, so you go from potassium, calcium, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. Those are all 3Ds. And how many D electrons can you have? Well, you count them. They're 10 right there. Okay, so you got 10. Then you get to gallium. And now we're back to the Ps, the 4 Ps. We have 4s, 3d, 4p. And you go gallium, germanium, arsenic, selenium, bromine, krypton. That's 6 more. Okay? You can also keep track of your numbers. Up to krypton, we get 36 electrons, right? So we're not there yet. And you can tell you're not there on the periodic table either. So what comes after 4p? Well, we jump down to 5. Period 5. The first is 5s, rubidium and strontium. Okay? Then we get into the transitions again. Now we're into d orbitals. All the transition elements are filling d orbitals. So we drop down 1 principal number back to 4d. And then we go across yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, and cadmium. That's 10 more. Now we're back to 5. Right, 5p. I'm going to drop down here. 5p is next. All right, 5p, cadmium. Indium, 10. Just 2. Okay? So we use the periodic table to do our electron configuration because we know how the periodic table is structured. Right? So which one of these is, well, if we look at the back, 5p2. A, C, or D. A, C, or D are possibilities. Right? Then we come back this way from 5P to 4D10. So C is out and A is out. So it's probably D. And then you can check it to be sure. But if you're in a hurry on an exam, then you got your answer right there. D. All right. Now, what if we were to draw this shorthand? What would we go back to? Well, we back up to the left. Right? We go through these two, then we go through those 10, then we go through these two. And this is where we would have a complete set of orbitals. And that would be a noble gas, which would be at 36 would be krypton. So if we said krypton at 36, and then beyond that is 5s2, 4d10, 5p2. That would be our shorthand version. And that way, we would have how many valence electrons? This one's a 5, that one's a 5. We have 4 valence electrons. The highest principal quantum number tells you which ones are valence electrons. All right. All right, I spent enough time on that one and we're out of time. So that was 44. Let's see. Let me make a note. We'll pick it up with 44 on Tuesday and finish it off. 44. Yeah, we got a ways to go, so we'll need the time. Let's see, that was 44. I think beyond 44. 46 is the next one. So I'll make myself a note. This is where we'll pick it up on, let's see, this is the 19th, 24th.